Hello everybody, how are we all doing? Welcome, welcome. Welcome to another stream. How are we all doing? There we go. So, yeah. Show a baby monitor there for the baby. Yeah, so you might hear the baby in the background because he's trying to get to sleep. Oh, we'll open up that one. Hey there, Captain Chica. How's it going? How you doing? How's it been? So, yeah. Last stream, what did we do? Last stream, we got the LOD system working, rendering, but there's problems. There's too many balls, too many spheres. This is the highest LOD, and they're not fit into the screen tiles. We can always allocate more. So this is them fit into the screen tiles, I think, but maybe the ones at the back are not. I don't know. Looks a bit off. But they're about pixel size anyway, I think. These ones are so small. So essentially when we zoom out this far, there's not there's enough spheres that fit into the big array that stores all of the spheres for the tiles. And if the closer we get, the spheres they get duplicated into too many tiles, so therefore there's so many duplicates in the big old array that it just sort of can't fit them all, and then we get some graphical glitches. You found some weird programming language the other day? Oh, yeah, there's plenty of those out there. Plenty. So I've been doing some thinking off stream, how to fix this problem. The reason why it's partly happening is because we don't have any occlusion testing. So we don't say, hey, can I render this cluster, or hey, can I render this sphere? We just try and render all of them. We try and bin all of them into the screen tiles. And this is not what we want to do. We want to have some way of saying, can this thing definitely not be rendered? Right, and if it can definitely not be rendered, we don't want to render it. And it saves binning it into screen tiles and doing more computation. So I've been crunching some numbers. I've been looking at the current performance. I've been thinking about other solutions. And part of me was thinking I could just move on and do a BVH like we did in the past. We are definitely going to still be using a BVH, right? A bounding volume hierarchy in the future for indirect for non-primary rays or secondary rays and stuff. But I'm trying to speed up the primary rays, the ones that come from the screen, and we do the ray tracing. And those ones, so the way I've done some performance tests in the past led me to believing that bending them into screen tiles is going to be better. But then I was crunching some more numbers, and I was thinking perhaps actually these numbers are probably around about an order of magnitude too many for this to be true. So basically what we have is a 256 cubed space. So that's 16 million spheres. So effectively this thing that you've seen on screen is nearly 16 million spheres. So you're already binning those, right? So it's probably about 10 million, right? Maybe more than that. And this far away from the camera, when we're looking at it, it really flickers the points, and I don't know why. But it goes from about 2 milliseconds to about 5 milliseconds, and that's just for one instance. And again, this is before we do any occlusion, culling, or anything like this. So I think one thing that I want to do is I probably want to scale back how detailed these things actually are. And we're probably going to go from from 256 cubed to 128 cubed for a volume. And so we're going from 60 million to 2 million. And this should be okay. So our clusters are 4 cubed, right? So 64 spheres. So basically you fit 64 cubed number of clusters in a 256 cubed area, right? That's 64 cubed, right? Because it's 256 divided by 4. So that this is how many clusters we have to process an occlusion call per volume if the whole thing is filled. Whereas if we did 128 cubed, that is 32 cubed, a lot of clusters, right? And then it's only 32,000 from 8 times that, which is 256, right? Okay. So part of me's thinking we should scale back our max volume size to probably 128 cubed, and that's probably still fine because if you take like a meter area divided by 128, that's like 8 mil per sphere. So yeah, I think it was just a little bit too crazy doing 256 cubed. Oh my boy. But yeah, so that's the plan. We're going to start off by scaling back the number of cubes and or number of spheres in each volume, and then we're going to do some occlusion culling, which we're going to after that. We're going to our plans. What is this language? Fusion Lang. This just looks like C# or Java. I don't understand. Quite okay image, okay. Yeah, I like quite okay image. This is basically Java. Alright, they got a hash there for some reason. And an exclamation mark. I know what the exclamation mark does. Or this hashing question mark. How do you translate high? It's not too hard to translate high level languages to C. Because one, they're not even like that much different from C anyway. They might just wrap stuff in pointers and stuff. Ugh. Ugh, look at these buggers. Man. Getters. I do write getters, but at like a system level and not a class level. Yeah. I'm not sure why people would just basically make a new language just to make a new Java or C#. You know, it's just silly. So how do we downgrade the how do we downgrade our size of our clusters and that? Well, it's pretty simple. We've just got constants. So we just change the constants. We've got to change a few of them here. Otherwise we could be in a pickle. So somewhere from about here going down. We're still having 64 clusters in spheres in a cluster. The clusters are not changing, it's just the number of clusters within a volume. So max cluster nodes. So I need to recompute this basically. So it needs to be one shift left. Yeah, so 1 cubed. So it's 1 plus 1, oh, my days, 1, what? Since when did that enter key do that? 1 plus, then 2 cubed, 8. 3 cubed. Uh, 27. 4 cubed. 64. I just realized that it's completely wrong. It's shift left, isn't it? Damn it. So yeah, 2, 1 shift left. Yeah, so it's 4 cubed then. 64. Then 1 shift left, 3. 512. 1 shift left, 4 cubed. Then 1 shift left, 5 cubed. Excellent. So that's that's the max number of clusters on the highest LOD now. So I've only got like 5 LODs now. Wait. 6. What have I missed? 1 shift left 2. 1 shift left 1. That's 2 cubed, isn't it? Yeah, we missed an 8. 2 cubed. Yeah, there you go. 6 LODs, so we've got to sum all these buggers up. And that'll be the maximum number of cluster nodes. So 1 plus 8 plus 64 plus 512 plus 4096 plus 32768. Alright, there's our new maximum number of cluster nodes. It's way less. It's 8 times. It's probably just 8 times less. No, it isn't. No. So there's that thing corrected. Max volume spheres. So 256 to the power of... Where is this constant even used? Because it's not really the max number of spheres. It's like a sort of a... Is this even used anywhere? No. Probably get rid of that then. It's kind of like a rough guess. Oh my days. Let me just go and calm the boy down a bit, give him a little bit of a run, a little bit of a... Yeah, let me calm my boy down a bit and see if he goes back to sleep after that. I'll be right back. Right, hello, welcome back everybody. So where was we? I was trying to reduce these numbers, right? So which one did we just delete? Here. Okay, good. Maximum number of nodes. What? Here's already one which is max number of nodes. Oh, is this like a rough? That's not good. That's not a good constant to have also. Let's search for that. Right. So here we're probably going to say this is one is like max cluster nodes count. So this is why you're building it. And this is when you have right, max volume constructor cluster nodes count. That's a different thing. Thank you for the follow, appreciate it. We're not too far off 4,000, I think. 4,000 followers now. Get in there. Nearly there. Right, so this one is the maximum number in a volume after it's been compiled, basically, because of simplification and all this that goes on. So it's kind of like it was kind of maximum. So instead this would be 32 to the power of 2. So squared times 6 times 2. Why times 2 though? Because you've got... Yeah, I don't know why the times 2 is there. What's that? Oh yeah, to have 2 layers. Yeah. So basically this gets you... where's the... I've got to rub out where it says 256 now. Yeah, so it's sort of volume. It's filled with clusters which are 4x4x4. Should use the eraser now and get rid of this. So now we've got a different number. What we have is 1. Oh, he actually went to sleep. What a good boy. Yeah, 128. Sorry, let me just go and check on my baby for a minute. I just want to make sure he's okay. BRB. He's just gone to sleep. Right, it's okay. Can't quite make him out on the webcam. Is there? Alright. So now we're doing 128 cubed. So what was I talking about with these constants again? Yeah. So this constant here is basically saying like, if we constructed this volume, which is 128 cubed, um, it's where's the in 3D, I imagine. So I can imagine you've got 64 clusters going that way, 64 clusters going that way, and 64 clusters going this way. A cluster is a 4 by 4 by 4 set of spheres. So the idea is we only store detail on the edges, and anything that's sort of like if you have clusters which are surrounded by other clusters, they kind of get deleted, and only a lower level of detail one sticks around. So essentially, if you have the maximum filled space, which is 128 cubed now, filled with clusters, theoretically you're going to probably have you'll have a whole face filled with, you have each of the 6 faces filled with clusters, right? And the ones that are in the middle just kind of get bigger as they go into the middle, right? So the way I've sort of done it, some rough guess, is the number of clusters on each face cubed, and then times by 6 for each face, and then yeah, and then times by 2 for the middle ones, for the lower LOD middle clusters, right? So it's just a rough guess. So we can use this as a way to sort of like say, well, we're going to support probably up to 1,000 volumes. So we can just sort of pre-allocate for that. And you can maybe fit more than 1,000 volumes, depends how filled they are. So we just need to calculate that number again because we've reduced it from 64 cubed times 6 times 2 to 32. Squared, I meant. Squared times 6 times 2. Oh my days, that went off the rails quick. Times 6 times... Right, 12,288. So that's 8 times less, I imagine. Again, these numbers are probably just 8 times less because of 3D. Yeah, so full volume still stays the same. Clusters at highest LOD. There's one shift left 18, which gets us that. Yeah, that number there. So I think it's one shift left 15 now. Oh, for crying out loud. Yeah, that's the number. Because times 8 is this number, which is how it used to be. So it's 15. Cool. That's good. Maximum volume dim, 128 now, right? How many clusters along a single dimension in a volume? 32 now. Right. I think we're good. So that should be all the things adjusted. Okay. Right, so now we rerun this. It shouldn't crash, but if it does, we'll be right back. Oh. Alright, so now we're only seeing like an eighth of it for some reason. Is that because the calculations now are a bit off? How can we be seeing an eighth? Oh, I know why. Because the coordinate system is not normalized. It's in spheres. Maybe this is a bad idea. Maybe it should just be normalized. Yeah, why isn't it in normalized coordinates? Why am I doing this? Yeah, why don't we shift this over to something like fixed point. Oh, but then I'm using fixed point, aren't I? And then moving to and from fixed point. Like, why don't I just use like I guess this is like a 16-bit. Wait, why am I using fixed point again? Oh, yeah, because I was hoping to cram it into 16 bits. Yeah, why don't you use a 16-bit integer and do some sort of like multiple of that or something? Yeah. Right, we should change this. I just don't know if we should do it now or not. So now the middle is 64, basically, in the... Yeah, when we do another iteration over this sort of like edit thing, we're going to change that to normalized coordinates. Target LOD is 6. Now, I wonder why that actually worked. Right, so now what we're seeing is the highest LOD. Why does it work at 7 though? That's a bit confusing to me. What does the target LOD do in the shader then? Oh, it mins it. It mins it to the maximum LOD. So that is why that works. Alright, so now we've adjusted this. We've got 8 times less spheres and clusters now. So I think this tile binning strategy can be fine now that we've got 8 times less. So what we're going to do is we're going to do some occlusion buffer now. So I'll start speaking about why we need this occlusion buffer for this approach. So as I mentioned earlier, this graphical glitch that we're seeing is because we've got one big array where all of the spheres are allocated into. So initially they're in this sort of like, let's get to the drawings. Initially they're in this sort of like cluster tree system where you have this sort of LOD 0, so this is one cluster, so it's a 4x4x4 set of spheres, and it breaks into an octree of children, which are a higher level of detail of clusters. And so essentially you can take a 2x2x2 of spheres, and the lower level of detail will be around it'll downsample into one sphere in the lower level of detail, right? So basically, when we try to render these, we take the clusters and move them into view space, and we try and see if they need to be rendered. Yeah, so we start from the root of the tree cluster, and we go over all L0s for every instance that needs to be rendered. We see if this is occluded, and right now it never is occluded because we haven't written the occlusion buffer yet. And then if it's not occluded, it will then see if it's the right height in view space. If it's the right height in view space, meaning like not subpixel, then it will try and render it. If it is, wait, no, that's the wrong way of saying it. If it's subpixel, it will stop. But if it's like bigger, if it's big enough to then go down into the children, it will then go down and try and render the children. If it's just about big enough to render on screen, it will render this this LOD. So then it will try and render the children and do the same thing over again. It will check to see if the clusters are occluded or not. And if they are, it will stop there. And it won't carry on down to its children or try and render that cluster. So essentially this method allows us to potentially skip thousands of spheres and clusters if they're occluded by other volumes. Yeah, by other volumes or clusters. And then after this, after we found our clusters, we then bin them into screen tiles. Here, by seeing, the cluster is here on the screen like that, filled with spheres. And the cluster can be transformed in weird ways to the point where it could even be each corner can be transformed in a different way, in a sense, making it kind of an odd shape. So all the spheres could actually be ellipsoids, basically. So we see which sort of clusters it goes over. We'll probably get a screen bounding box for that. And check to see if any of these ellipses fall inside those tiles. If they do, they get added to the array for that tile. This tile has like an array of 2 spheres right now, right? And then when we try and render for this pixel here, or this pixel here, rather, it's inside this tile. So we'll go over this array of spheres to see if we hit any of those spheres, and if we do, we return the pixel color. So the way this system works is it goes, when the cluster says, hey, I go over all of these guys, it marks down and says, hey, this thing takes at most the amount of spheres I have in here. So this might have 64 spheres. So it goes, okay, this tile has at least 64 spheres in it. And it'll do that for all of these guys. If you have a bunch of overlapping clusters, these will get different numbers, obviously. And then it'll go over and do an allocation setup where it will actually allocate these from a massive array. So you have some massive array which holds all of the spheres for the whole screen, and essentially these will be sub-allocated. So you have this is for tile 0, this is for tile 1, and this sub-array here is for tile 2 or whatever, right? This is be tile 0, 1 or 2, and within this range of memory you can allocate some spheres in there and some spheres in there. There'll probably be some room at the end for because we just over allocate them, basically. So a problem was happening where we was filling up this big array because we had too many spheres filling up, being placed into multiple different tiles, basically, and filling up the whole thing. So one way around this problem of even getting a cluster to look over, even spend the time and allocate and say it needs more memory here, and even going further and saying, hey, these spheres need to actually be put into here, we need an occlusion buffer. Is the CM GUI? No. I didn't use... This tool here is Milton, so you can just like draw stuff in it. We haven't seen any UI for my application at all. But there is a UI library in there. Or a UI subsystem, and it is an immediate measure UI, but it's not MGUI. Or DIMGUI, if you will. Yeah, so we need an occlusion buffer to basically skip clusters. And how we're going to do that is, I think the best approach is to go over this tree, and we need to find the biggest set of axis line bounding boxes which cover which are filled with spheres. And then those will be our occluders. And then we can take those occluders and render them on a low resolution buffer. And we can use that as a rough guess to see if something is occluded. And by I mean rough guess, what that means is if you have some sphere and you have this sort of information, this depth information for this sphere around where the sphere is being rendered, what you want to be able to test is this thing absolutely occluded for definite? And if it says yes, it absolutely is. But if it says no, it might mean it is actually occluded, but we couldn't quite tell, or it's just not occluded at all, right? So that's where it's rough. So so we always have to make sure that we are correct when we say yes, it is occluded. If not, you start getting artifacts, right? Glitches and stuff. So what I want to do is generate some quick occluders. We're going to improve the occluder algorithm later. But yeah, we're going to, yeah. So I need to find where we so this is where we build the tree. Here we go. So this is the make persistent. What I need to do here is generate some occluders. I don't know if I should do that before. So what we want to do, maybe we do it before the make persistent. We need to generate some occluders where we say, we go down the tree and we want to just look at the spheres and just see where I can put some axis line bounding boxes over a whole bunch of spheres or something. And I want to encode that, so probably somewhere here actually. So I think I want to copy this. So I want to call this like make occluders. So I don't know what the maximum number of occluders are going to be. So do you want to do this actually after refine or after make persistent? So you go down the tree, find the maximum occluders. Ideally you want the biggest area. So perhaps you do it here and do a second pass which sorts it and finds the biggest ones. Yeah, but we'll probably do that later on. Yeah, so let's just get the initial part of the shader going. So do the same sort of system we've done before. We're going to essentially call this shader one for every LOD, and it's going to go over all of the clusters within a level of detail, one dispatch at a time, and generate the occluders all of those levels of detail. Then maybe it doesn't need to do any sorting. Right. Maybe you can just do the first so many. They kind of would be random though, every time. They won't be persistent. So maybe you can sort them. Yeah, sorry, they won't be deterministic, that's what I meant. So what you want is like probably a deterministic set of occluders from the same input. So we'll probably go down the tree, find more of them, and then sort them and get rid of the ones which are the smallest. And we'll probably do a secondary sort condition as well. So they become in an order, in a deterministic order. So we say make occluders, we want the process ring buffer, so we need to make one of these up. Make occluders. So this is our ring buffer. Yep. Our ring buffer entries count looks good. This is the make persistent code. This one is the where's the refine? Right. So make persistent ring buffer goes in there. And there. We don't read on the occupation map. We simply just need to process the nodes. And now we need to put the ring. We need to generate. We need to know where our occluders are going to go. So we need like a new data structure. There's a cluster node. So we want to have like a volume occluder, if you will. So this is something that is going to be in. So probably we could. So you only need 7 bits. Is that right? Maybe you need 8 bits. Because we need the 128 cube space. We need to be able to put it on. Oh no. Yeah, we only need 7 bits. So I think we can get away with literally like one of the like 4 bytes basically. So this would be the occluder. And essentially what you're going to store in there is each byte is going to have like a coordinate. Wait a minute. In 3D though, isn't it? Maybe you need a bit more information. Yeah, you need 7 bits times 3, so 21 bits per. See, you could pack it down into like LOD. So LOD only needs like 3 bits, I think. You need to go to bits 0 to 6. Then you could probably store. Then you need 5 bits. Yeah, I don't think that saved any information. Maybe it has. So you need 3 bits to the LOD. 5 bits. 555 for an XYZ each position. What color theme is that? And font? So the font is Liberation Mono. And the theme is there. It's basically a based on another theme, and I sort of changed it a bit. I basically really liked Iceberg, but I wanted like a red version of it. So I looked around. I really liked Iceberg for Vim. And it's like a bluish one. And I used this one for a long time. But it's kind of got, you get fed up with themes. But I liked how this one was only a few colors. And it wasn't, like a rainbow editor. It's just very sort of a few tones. So one like this, which kind of like red and orange, and I found the two colors. I found one which was basically what I wanted, but it was slightly off. So I basically modified it a bit. Yes, Zoganda. No clown fiesta. Is that? Yes, that's what I'm talking about. Like, I swear you use so many. There's so many themes out there which just tons of people just use, where they're just like, it's a rainbow party. Yeah, this ain't bad. I like the subtleness. It's got a bit of green, got a bit of blue. I think maybe some of the text could be a bit brighter though. But yeah, I do like the idea of it though. That's great. Our numbers are red. Let's see. So you need 5 bits at most to talk about the possible. Or you need 7 bits still. No, you still need 7 bits. Yeah, 5 bits say what cluster you're in. Yeah, then 5 bits to say what cluster you're in, and then maybe just 2 bits per. To say what spheres within the cluster. So you'd effectively need all those bits, if you will. So that's 6 plus 6, 12 plus 15. But that can fit in one word. Yeah, that can all fit in one word. It's a bit packed though. Like it's a bit overly packed. You can do it. You can fit it into a 32-bit integer. Just wonder if you should. Versus just storing. Let's just store it as readable, but we can pack it down, right? Just an idea though. So basically you want, you effectively want like a, is it a center position though? The occluder. Or do we want it as kind of min-max? Yeah, center position and then half extent, half dims. Yeah, so we can actually pack it down into one U32. We're just going to use 6 here now. But yeah, it's interesting. So here you can say LOD, 3 bits, cluster coordinate, XYZ, right? Then this would be a sphere coord, sphere coord min, min max. Right. To pack this down into a single U32. Here is the bit bits. I wonder how much better it actually is. We just maybe save memory, maybe it'd be better, I don't know. Maybe it won't be. Depends on how many of these we actually have. So this volume occluder, where is it going to live? Should probably have a separate buffer. I don't know how many of these occluders that we want, but let's just... Volume occluders. Oh. Right. So you need this volume occluders here. And then... Should we have them in a separate array? So I wonder if we could just stick them in here. We could just have a volume occluder. And you have some sort of max occluders. So in our lovely bunch of constants, maybe we support up to 256 occluders. Maybe it's too many. Maybe 32 is fine. You need 32 at minimum, I think. All right. So we're going to construct that buffer as well. Constructor occluders, volume constructor occluders. So what's the maximum number of occluders you could possibly get in a constructor occluders? Oh no, the boy's waking up. Oh boy. So let's say when you're in the volume constructor and sort of constructing the initial thing, to find the best ones, maybe we'll do 1024. So we'll like to fill up 1024 of them, we'll sort them, and find the biggest ones. All right. Right, so that's how we set up that buffer with that constant instead. Excellent. So now let's continue to where I was going to kick off those shaders. So we've got this volume constructor occluders thing. Make occluders, here we go. So what I need here is this to be passed in. So it's going to be called the occluders. So we're just going to bump them on there basically. So this would be called cluster tree make occluders. It's going to be dispatch indirect. at LOD. This one will be set up LOD, I think. Yeah. Okay, so this is called once per. This shader is called once per level of detail. Does the whole, all the nodes in it. Tries to get all of the occluders for all the nodes in that level of detail before moving on to the next one. Right. So now what we're going to do is go into the shader code and actually make a very simple version that we can debug and just see. Oh, what did I do that? Let's copy paste this. All right, process ring buffer, bunch of cluster indices, then all the occluders. Read write, volume, occluder, and then occluders. Boom. So now we're going to find this refine LOD shader, and there's two shaders to copy. So I think I want to copy probably all of that, and we're going to go to the bottom of this one. So there's this one that sets it up. It sets up the ring where to process from the ring buffer. So make occluders. Refine. Make occluders. Boom. Right, so where we see the word refine, we've actually got to replace that with make occluder. So this is going to set up the ring buffer so we can read from it in the next dispatch. Because this shader creates more work for the next iteration. So this shader needs to be called before this one is called to sort of set up the next iteration. Because we're going to essentially write to the ring buffer in this and also read from it. So we're going to read from it here, from this read base index. And then we are then going to push onto it as well. Where's the push code? Here. So we want to save. Yeah, I don't know. Do we want to have a 32? What are we doing? Doing 32 nodes per thread group? One node per thread? Yes. Because I don't know if you're going to get any benefit processing each sphere and checking. Yeah, I don't know. So we'll just keep it one per thread. So here we'll just say, okay, if it has any children, we need to push all the children on. Wait, the refine is starting from the tail though. Yeah, the refine is starting from the bottom of the tree. That's not a good example. Where's the other one? Yeah, I guess it just needs a for loop. Yeah, this is what I need. So we get the children bit set. Then we get the least significant bit. That gives us the child index. So this would basically be 8 bits. And every time we iterate over these, we'll get all of the bits that have been set, the index of all the bits that have been set. So we can iterate over all the children and miss the empty spots. But you have to remember to remove the least set bit every iteration. So what we're looking at trying to do is place on, that's right, isn't it? Yeah, insert into the, wait, did I miss that? Oh my days. So get the number of children. Just adjusting those variable names to be the ones that are for this one. So get the head index, get the new insert index. Buffer overflow. We're never gonna, it's a ring buffer. Oh shoot. Oh yeah, it's never gonna overflow that. We know that for sure. Yeah, because we've got a big enough ring buffer in this case. Yeah, so you get your base insert index, iterate over, insert and wrap the index around back into the ring buffer. Insert that for the next time we call this shader. Okay, so that's how we set up that. So we just got to insert the code now which makes the occluders, and that goes here. So this is all the code that should do all the ring buffer logic basically through each of the LODs. So this gets called dispatch for every LOD one at a time. First time a dispatch over all of LOD 0 nodes, and then all LOD 0 nodes will only push on LOD 1 nodes. And then this shader will get called, sets up the ring buffer again properly so that the base read index is in the right place, and then the tail index and the head index is in the right place, I think. Yeah. And then our tail index is where we'll insert our next lot onto, and we'll read from the base index. So I'll read LOD1 out, and this will push LOD2 onto the tail. Okay. Very good. So let's test that out. First things first though, we do actually have to add these globals to the global buffer. And they do have to get initialized. So we need all this ring buffery stuff. So it says refine now, we replace it with make occluders. Alright. So now the one thing that's not done is that the this has to actually be set up in some way. Like the refine, I think we need to make another shader basically. We need one like this. The make persistent has one. So this is called make occluders. Make occluders setup. So what it's going to do is it's going to make sure that the head and tail of the ring buffer is set, and we push on the root node. And I think that's it. Make occluders. So yeah, it puts the root node on the ring buffer. This thing makes sort of this root node be at the read position, where the base read index is equal to the head. And then the head is now equal to the tail. And the same means when we call this shader, we'll be reading off that basically. I think that's it. So that's got to be dispatch index. Cluster. Sweet. Oh, dispatch indirect arguments. I completely missed that. Make occluders dispatch args. Make occluders. So the dispatch arguments. The number of clusters to process. Divide. Core divide. Round up. 32. Max 1 is at least fire 1 off. Alright. That should be the system set up, but it's obviously not going to do the occluder magic. Just got to fire off the initial shader. So this is going to be let's just get that right. So this is going to be the setup function. So dispatch cluster tree make occluders setup. That's the one we literally just made. This one needs probably just the and the ring buffer maybe. Let's just put them all in there, I think. Where's the sync code at? Let's put that in there. Nice. We need to launch one of those. Yeah, good. The dispatch, the indirect arguments. Kind of missed that. It's not refined. There it should be make occluders. Nice. Hit F5. Let's get this thing compiling. Why is occluder? Okay, occluder obviously needs to be declared before. It'd be nice to be able to pack that down some more. Occluders. Damn it, why? Oh, that's a texture 3D. Whoops. I mean a buffer. Cool. What is this doing? Cluster in instance. Oh, I took this code from the wrong place. That's when we do our processing clusters code, which is not inside the build, the building clusters code. So this is when we're building the clusters still. We're inserting a new pass, which makes the occluders in local space of the object. We just need to pass in the cluster index of the child to put onto the ring buffer for the next time we call this. Right, so let's give that a go. If the stream dies, it's because of the AMD drivers, and I've crashed the GPU. Right, we should be back. Seems to have not lost that. That's good. Right. So we've got to find our problem. But hey there, Ray. How's it going? So yeah, I don't know what we could have done. So we've got to check line by line now and see what that problem is. That's not good. Yeah, we're calling all the right shaders, I think. Yeah, so we'll go over each shader, make sure it's all A-OK. Did I initialize this? Yes. Did I initialize that as well, didn't I? Wait, let me just check on my boys. Just got his the blankets on him a bit funny. Let me just it was alright. 2 seconds. It was alright. It's good. Okay. So why was this crashing? Let's investigate. So we've got this sort of like setup. Alright. Excuse me. So this one is very simple, right? It just takes this in. It just needs to write to the process ring buffer, and it writes to the global buffer, which is globally accessible, so don't pass it in via the push constants. The occluders don't really need to be there, neither do these as well, but we do it anyway. The process ring buffer is not read-only. Read-write, isn't it? Do we do silly stuff like that, really? But yeah, no, that's not going to crash this driver. It does on the Windows one. The Windows driver on AMD doesn't like that. You get that wrong. Wait. I forgot now. No, it crashes in the shader. It's wrong in the shader. Or read writes. Yeah, it crashes on the shader, the AMD driver. But this could be wrong to the point where we read from a buffer invalid information and then take that and then do an invalid index into a buffer or something. So potentially that is a problem too. Alright, I think we're fine there. So this one is okay. The code there. Double checking the dispatch again, so it's a bunch of read writes on the right buffers. Yes, the right shader. Wait, I'm reading the wrong one. That's the right shader. Bunch of read writes, yep. Setup one, yes. One of those, and there's your. Yeah, so it's uploading the constants fine. Now we're going to do one for every LOD. If I can't find the problem, we'll probably just change it down to 0 and see if it crashes again. So we're launching the setup LOD version, just setting the LOD in there. It's just a reusable push constant thing. This one just writes to the globe, reads and writes to the global buffer. We did read write on that, didn't we? Yep. Then get the number of clusters to process. This could be funny. Oh, we never initialized any of these properly. Refine, dispatch. Make occluders. I don't know if this was the problem. But, you know, we was missing 1 in the Y and Z. And those was uninitialized memory. Probably 0 though. So yeah, that is an issue. I don't know if it was the problem that's causing the crash though. Could be though. So max of this number divide up random. Yep. So it's got to at least be 1. Divide random up of that. Good. Because we do 32 nodes in a group, so we need this many groups, right? Then yep, these are the right, that's correct. So this one's fine. Let's double check the dispatch code again. Yeah, that's all right, it's everything. This one's fine. Next one. So these go, they're wrong. Well, they're not even used, I don't think. So these are correct, they're reading from the make occluders thing. Something I might do is get rid of this code and just see if it still runs as well. Clusters to process count, sure. That's fine. Plus dispatch, construct a ring buffer, yep. That is different, that is wrong. Right, these are different numbers. So that could have been causing us a problem as well. That's fine, this is fine, let's make occluders, make occluders. Yep. Process ring buffer and let's take 1, yep. Okay, so this all should work now. Let's double check the dispatch quickly. Read write on all the boys. They're the right buffers. Global buffer, make it clear to yes, that's the right thing there. And okay, so this should work, TM. What I might do is yeah, right. Let's run this and give it a go. So if the stream crashes again, you know the drill, I'll be right back. And it's AMD. But anyway, here we go. Alright, we're running. Perfect. So we fixed the problem. So here's our, you know, thing we're trying to build the occlusion stuff for. It's so glitchy because it's just filling up all the stuff. Maybe we can remove the glitches just by upping the number of spheres we have. Okay, so I want to bring back the music because music is good. Bit of Stone Rebel, now that we're not crashing again. So here's our group of shaders that are now running. Here's the setup one initially. Then there's our oh, why is that taking 1 point whatever milliseconds? And our refinement is taking. So clearly, because we've got that for loop in there, it takes a bit of time. Nah. How should it be taking that amount of time? Like, it's basically doing nothing. Like, this would not even be existent at doing anything. Oh, it's doing this add. What's the ring dot in it? Oh, hey. It's doing alright. So basically we're trying to all atomic add to this every time. And we don't need to do that. So that'll help out a whole load with the performance. So that's probably another reason why the other shader could have been slow. That does the preparing clusters for rendering. Where is that one? Yeah, prepare clusters for render. There's a yeah here. We don't even do that. No, we do. We say if it has children. We've already done it here. Okay, that's all right. Anyway, if we run this, then what we'll find is it will actually be faster. No, it's even slower now. Why is that? Why is this one slower than the refinement? The refinement's like a beefy shader. We can do some printing. But the refinement kicks off on the biggest LED, and that's fine. That's like barely anything. And why it's at 3 millis? Right, then it wasn't 3 milliseconds here. Still though, it's still expensive. I think there's some problem where I'm running OBS at the same time, so sometimes the shaders are a bit long. But that is questionable still. Um, um, let's print out the number of clusters that we're processing. Let's see if that number is consistent. So 116. Right, so there are numbers. Drop them in here. So let's find them again. Here. Oh, they're slightly different. Why are we why is it not deterministic? So I think we have a bug where the tree isn't being generated the exact same every. Yeah, we have a bug in the generation. That needs to be hunted down. It needs to be hunted down. So at least we know that now. So I wanted to up the number of spheres so we can not have a buggy view. Where's spheres cap? It's the thing we use at the moment. So I've done 800,000. Let's do 1 million. Hopefully that's enough. Yeah, see, they do jump around a bit actually. And yeah, it's really annoying. I can't get this. We should be able to do 2 million, to be honest. It's just memory. Problem is the spheres overbin into different tiles. That's the issue with them. That's what we're trying to fix this occlusion. Let's do 4 million. It should be enough. Oh. Right, we over allocated. Alright. Let's try 3 million. Yeah, I've over allocated the upload buffer or something is a bit too. I think I did anyway, something's buggered. We'll stick with just 2 mil for now, so we can't still view it without the occlusion. Getting there though, it's just a bit flickery and dancey for some reason. And I think that's the bug we've been encountering in the building code. Alright, so should we just build our occluders then? Some basic occluders. And or should I fix this bug? I want to look at fixing this bug actually. Do we encounter this problem in when we generate the initial tree? So when we generate the initial tree, do we encounter it there before the refinement pass? Right, let's drop that in there. So 186448. Right. Next one. Okay, so this is consistent. So it's not this thing which is causing the breaking the determinism, is it, right? So with every frame this is identical. So that means probably in the refinement pass then, should we have a look at that one? Because that comes after. We construct the initial tree first and then we refine it and produce all the lower levels of details. And this one probably is missing a barrier. Oh, for crying out loud. Refinement, plop that in there. Yes, this one works differently. It goes bottom up. So it does the highest to lowest nodes basically. Because it processes all the high detail first and tries to lower it down as it goes up the tree. So this one looks the same. Maybe that's the same one, I don't know. Let's go up a bit more. 86448. Okay. Right. So the refinement is not yeah, but the refinement must break the determinism still, even though it's not receiving invalid. So where it breaks the determinism then is how it's deleting the nodes, I guess. So let's just double check. We're using this LDS. Memory, where's the LDS at? Do we use LDS? No. What is this one? Yeah, that's the tree construct. Right, something's fishy then. I think we're not putting an atomic read. And we're getting old data or something. I don't know. Double check anything that's sticking out. Well, I've got this printing code, doesn't need to be in there anymore. Child node. Child node's been in process before. You will. It should be, the cache should be flushed, so it should be fine. Because the previous dispatch that writes to a child node. Create the lower LED sphere, you bit all that on, right? So when you write to this node, you should be using atomics. Read out the child node. Oh, but you write to the child node. Oh no, you load from it here. Number of children. Right, interestingly, we're not doing an atomic load here. Let's put an atomic load on here just in case to see if that was the problem. But then you're not doing an atomic load there either. Hmm. Like, where are you modifying the child anywhere else? Then modifies the current node and gets rid of the children bit set. And it clears the spheres to 0. Hmm. Yeah, you should be accessing those. Yeah, it should be okay. I don't think you need the atomics here, not gonna lie. You've already gone and fetched the child node. So the thing to test would be, we'll do the printout here again. And we probably want to find a particular node which exhibits an inconsistency with the data, like it just changes every frame. Oh, there is a control barrier there. Interesting. So we remove the cluster from there. See, I don't see us working off any of the... Yeah, control barrier, weight, load, sub, anything else in here? Hmm. Yeah, I think that's okay. Right, let's print this out and just debug it. Oh, for crying out loud, what's going on? Right, I added that atomic load there, didn't I? That's atomic load on a local variable. Not a good idea. Alright, okay, so let's try that out and see if we get any inconsistencies. So 116.206.3332 or 3322. Okay, that's definitely changed. So past LED 1 is when you start seeing some changes. So one thing that we can do is we can disable when we do this and it removes the nodes. So let's make it so that we never remove any nodes and just see if the problem still, that sort of inconsistency still happens. So you got 16.192, 16.26, okay? That's different still. So the inconsistency isn't coming from when we delete a node. It isn't okay, so that means it could not be, it might not be caused. Because volume cluster refine, like this one always pushes on the parent node and goes up the tree. But maybe this is the first shader which goes down from the top, this make occluders, that we've just added in. So maybe the children, the code that makes the initial array of children is actually wrong. Inside the initial volume tree construct. So we do something with this children bit set, and we use LDS, so maybe this is it. So what is it then? Do some more. So this storing, load. Right, so let's see if there's any problems with this LDS thing. So the first thread, store in there and set it up, wait for the 2 waves to get here before you carry on. What do we do with this thing? Or just store it in there anyway. Cool, so nothing else happens here. It just processes all those ellipsoids and cuboids and fills the area. This happens within the wave. They're probably consistent. Yeah, so it's probably best to pick a cluster at a specific coordinate and just see if the children changes. And it's got to be a coordinate, not an index. So cluster chord. So we'll do like if that is equal to whatever, are my children bits the same? So read from LDS after you've written to it. I don't see any problem with this code. It seems fine. Right. So let's try this. If cluster chord dot x equal so what were we thinking for? So let's say 32. So y, z. Let's try that. Then let's do a GPU printf. And I want to just say found, and we'll print out hexadecimal. Children bit set. So, oh my days, it's not even a thing. Order cluster LED. Crying out loud, what was that? Well, I got that wrong still. Oh, I also completed the wrong variable. Oh, I forgot the and. Alright, let's give that a go. So we've got, did we search for found? Did we find found? Interesting. So it's called twice. But it's consistent. Hmm. What other variables do we have that we can use to debug this problem? Yes, you will get multiple that show up. That is true. Let's do a more common one then. Let's do a lower number. Like, let's just do 8. And we'll see how many times it gets. There'll probably be for every LED, we'll probably get 1. Now we'll see if that changes at all. Right, so they're all on there. I don't know what LED that was found at, to be honest. 8 probably wasn't a good one. 16. Because 8 was on the edge, and I think we removed those guys. The low LEDs. Oh, okay, still doing the same thing. Yeah. Right, I'm still not sure why it's inconsistent then. Between frames. So when we print this out and we go down the tree, it's different every frame. Why? We can't. So it starts changing at LOD what again? LOD 2 is different. But all we need is 16 to print out the children of 16 nodes. Right, because that one's fine. So why don't we look at LOD 1, print out all of its children, and just see where it differs, I think. Maybe that's the way to do it. Oh my days. That's a problem. Maybe I just found the bug. So the problem is we use the high bits when we construct volumes to mark if the node has been visited or not. So that could actually just be the issue. Right. Oh, I think we just fixed it. Okay. Well, I'm glad we found the problem. Yeah, 18643. Okay. So this, as you can see, was a bit error prone. So it's just a bit set. The first 8 bits are. I need to clean this up a bit, but the next 8 bits, so to mark whether that child has been refined yet, since we start at the bottom of the tree. And we use this so we can loop up from the bottom of the tree, basically. It's where we store information. Maybe it's better off lived in a separate buffer, so we don't have problems like that. And I can pack the node down better. I don't know. But yeah, that was not good. So it's counting more children than there were, inserting more children than there were, and then basically was getting extra nodes being processed. So that was probably then the cause of why the performance was so bad. Hey there, Sleepy Mushroom, how you been? It's been a while. So check the performance now. Yeah, this thing is a drop in the water. Excellent. Alright, that's what I was looking for. So now we can start making these occluders. So we're going down. This is called for every level of detail. Process all the nodes in that level of detail, and then the shader ends. Sets up the next level of detail, does it again. And it just keeps repeating until we've processed the whole tree. Let's get Milton back up so I can do the drawing. So the problem is we've got a cluster, and we need to try and figure out what are the best access line bounding boxes to fill up the space with. So you've got this So you got this cluster. Essentially, you're going to want to put a maybe these children exist and the rest don't, right? You want to put a bounding box that sort of is kind of in between them or something like that. So then this will be one of your occluders. And so if this is at like the first level of detail, that's like a quarter of the whole space. It's quite big. Obviously, as you go further down, the smaller and smaller that actually gets. So you want to build your little occluders like that, basically. But where I'm getting at is this is probably a bit of an effort to implement. So I want to just do it the quickest rough version. And what is that? Well, we're just simply going to say if node dot spheres bit set 0 equal U32 max, and so if all bits are on, right, if it's a full cluster, right, there's an occluder, and that's all we're going to do for now. So SV no, constants, occluders, we'll bump it on there. I've got to get a new index, an insert index. I'm good, been working on a 2D game recently, although this isn't the latest build, it's a project I'm working on right now. Awesome. Good to hear. Have a gander. Sleeping mushroom / program. Okay. Where's my pictures? Right, it's using OpenGL, I guess. Cool. Awesome. So you don't know some OpenGL. Neat. Rolling your own engine, I see. Yeah. And then glad. Fair play. I guess glad seems kind of minimal. Yeah. You can also hand roll your own version, it's quite simple. That's cool. Yeah, I think there's a X macros. There's a way to do a function load of X macros. I do the same thing with my Vulkan setup. With this one. Yeah, I'll drop a link in the chat. Essentially, this block goes over here. You can define your functions that you want to use in OpenGL and just do a function loader. Use an X macros. Yeah, this is it. I like this one. So you can literally just declare all the functions you want to use, and then just use X macros to like declare a bunch of global procedure type defs, and then actually initialize them as well. Or global variables, then initialize them. So it's pretty neat. I do this with my Vulkan code base. Ah, Render Goblin. Haha, I see. See what you're saying. Yeah, things about X macros, they're a bit of a hack, but they're kind of useful. And if you understand the trick here, it ain't too bad. So we need an insert index. So basically in our globals, what we're gonna do is have our volume cluster construct occluders count, right? So that gets instantiated to 0. Then you bump allocate it here. So you just go insert index equal atomic add U32, the address of that, and 1. Now we can fit in our occluder. let's look at the occluders. So a center position and a half dims. So we're just going to use the full-on yeah, what coordinate should I use? Yeah, I don't know why I'm not using like normalized coordinates for the whole thing. Right. Let's go up to the previous time we've used it. Cluster to get the LOD. Cluster chord at highest LOD, where's that? Yeah, that's what I want. So I need this. This gets me the cluster coordinate. So there's a center position. Which is kind of this. How big is the cluster in highest LOD space? So before then 8, then 16. So I guess it's just cluster dim 4 shift left, right? That'd be like cluster dim. Yeah. So the center position. So I guess the half dim is cluster dim divided by 2. Then essentially the center position is add E32 times 3 add S cluster coordinate cluster half dim, so that gets you in the middle, and then the half dimensions yeah, see, for now we're just doing one that fills the whole cluster, but there will be ones which fill different portions of the cluster in 3D, different axis line bounding boxes. So for now this will do. Right. So that's going to make all those occluders. We want to make sure that we don't go too far. So basically there's a constant, because you can overflow this thing quite easy. So we'll say, okay, we'll live this thing, make sure insert index is less than that, and then do the insert. Cool. So that should be everything that we need to have our simple occluders that we can render at a low resolution. Hey, Cranston. Kind of clunky on prototype. You have to stop, go through, add new bindings, reading the XML that defines the API, like Python, spit out C. Whereas you like. No, not really. The whole point is using X macros, right? It's just built into the thing. It's not that hard. Like in OpenGL, it's a bit of a different story. You have to define. You just look at the OpenGL header, and you can see the function prototypes and just get it set up. But in Vulkan, what's great about what they do is they include all the function prototypes inside the header file. So whenever you find a function, it's just pfn and they declare a function prototype for all functions. So you don't have to generate these like you do in OpenGL with X macros. So in Vulkan, it's actually like even easier, but it's still quite simple. Source GPU, Vulkan, back and internal, right. So all I've done is just got this X macro. See, in OpenGL, you have to put the types in here. Like, you'd have to put like, I don't know, VKQ or whatever, I don't know what it is. Or U32, you have to put the data types to your parameters. But in Vulkan, I literally just have to declare like, hey, this one comes from the DLL, this one is an instance function, this one's a device function. And then here's the list of functions, I just add it to this list. It's pretty simple. And then here's my global. And then I just say, okay, here's how you define those library instance and device ones. PFN underscore function name, then function name. Here's the list. Generates all of that inside this data structure. Just makes those fields in there and done. Then in my Vulkan code, so you don't need anything like Vulk or whatever that people use, because it's just, this is your own version, and it's just loads the functions that you need. Then when we do the function loading code, here's where we initialize the backend. We only want to load the symbols that come directly from the DLL. So we load the DLL, which is vulkan-1.so or whatever. Loads from that. Generate for all the functions which have this library, it's going to find the symbol, get the pointer and initialize it in that global structure, and then check to see if it exists, and if not, it failed to load it. And then you just got more cases of this where, hey, we've created the instance now, so we just load the instance functions with this get thing, right? So it's all pretty simple. Yeah, but why would, yeah. But the thing is, you don't want to have every single function pointer get loaded. Like, you only want the ones that you need. And this is automation. Eh. Eh. So I think we've got our occluders there now. Let's give it a go. Right, so apparently... Okay. So now what I want to do is... There'll be 1,000 of these. So maybe we should reduce that number. Let's just only do 32. And then... Or maybe 64. I don't... yeah, whatever. Now let's just see all these occluders. Oh, and if it built an occluder, maybe it shouldn't do the children for now. To do remove, process more children. If the whole cluster has not been made into occluders. Cool, so this means we only have one area which just gets shown. So now I want to do a lovely draw 3D OBB. So I just got to get the view from local. Oh no, we don't have one. Yeah, we'll put this in. No, we'll just put it in view space. No. Yeah, so we'll use so global view from world, so just be in the center of the world. Now we need to get this sort of like position in local space thing. Yeah, we need to get these. So what about this half clustered thing? Right, can we try that? Oh shoot, what is that? Cluster LOD dim. Right, then this one here. Okay, so this we should be debug drawing these occluders now. There they are. Right, they're kind of dancing all over the place. They're a bit small as well. We've not scaled them properly. But yeah, these are the occluders basically, and they're so bloody small. We should probably color them differently based on their cluster index, but they'll probably be like or maybe their position. Alpha's at the beginning, isn't it? Red. Oh. Alpha. Yeah. Oh, maybe they're just dark colors. Ain't nothing about Vulkan simple. Yeah, no, right. That is the simplest thing though, I promise. About Vulkan. We need to scale this. Can I just scale something else? What's that gonna do again? Offset and half dims. Yeah, we've got to scale the whole matrix. The whole matrix. Mole. So we want to scale it, right? Scale. Let's try that. Let's do uniform scale of 16. I don't know. Maybe it's the wrong way around. Right, they're a bit bigger. 64. Let's get made smaller. You made a new trailer and a goblet. There we go. Right. Now we can see we're getting some occluders at least. It's flickering though. So we probably need to do that sort of ordering thing that I was saying about. So what we've done is we've picked, so this is a blown up version of this. We're not quite seeing the full thing. Maybe it should render another one. We'll go okay with the first. If we're cluster index 0, let's just render the full thing. Give it like a yellow outline or something, I don't know. You know, we'll probably just put this code. No, but it wouldn't be full, would it? Right, what some of these do I need? Just all this, I guess. Probably plus that. Right, compiled. Give that a go. Right, there we go. So now we're seeing this is the full space, right? Representing like if you used to put a box around this sphere, it would basically be this yellow one, right? And then these, so as you can tell, there's some the clusters at the edge of that sphere are not occluders because they're not fully on, right? They've got they're missing pieces in our code. At the moment, only uses clusters with full occlusion. Wait a minute. Full occlusion with full set of spheres. They're the only things we're making into occluders right now, just because I want to test out the whole pipeline, and then we can improve this code. So the main problem with the solution we got right now is that it changes between frames because GPUs are not deterministic the way they dispatch and do things. So we need to probably sort them in some fashion. And then those are the ones that we keep. So we should sort them based on how big they are, and then probably how close they are to the middle, or something like this. On the X, Y, then Z. And then that way, they will be consistent and they won't flicker. And then those will be our occluders that we can test. You're gonna make a more exciting trailer. Hey, Campaign, how's it going? Yeah, I've seen your message, by the way. It's been, I'll reply to it soon. It's been busy. But yeah, how's things been? Oh, your game's changed a bit since I last saw it. Yeah, I think these similar photos. Is this the new trailer or an old trailer? Oh, you said you need to make a new one. It's a boring trailer. Okay. But I guess you don't have this stuff. Have you improved the game from this? Oh my days. So if you die, you blind your players with a white screen. That's fun. Collecting some more. Oh, you can put up walls and stuff. Nice. Build your own base. Nice, keep it up. Pretty honest gameplay. Everyone says that about my white screen. Okay, I'll fix that. Yeah. Yeah, it's really impressive though. Like, you know, seems like you're taking your game places. That's all by yourself as well. It's good. Hey, Sockham. Oh, I missed you when you entered. Are you doing OOBB physics? Oh no, this is only debug drawing. I'm not doing any physics yet. I don't know what I'll do for physics. It'll probably just be very basic, not gonna lie. It might not be a physics engine at all. It might just be height map stuff. I don't know. We'll see. So this needs to be placed. So we've got a buffer. No, we'll eliminate it to like, yeah, 64 in it. So we change it like 256. Yeah, we'll leave it at that for now. So we'll get a whole bunch of them. Like we'll have like 1,000 of them. But we only want to keep 32 of them. So when we do a make persistent and take a copy of all of this construct data, we need to sort the array. We need to sort this array of occluders. And then we sort the array of occluders. Oh, it is. This is just confusing me for a minute. So we sort the array of occluders based on that thing we just said, and then right. So let's make a quick dirty shader, which is just gonna do the most terrible sorting code you've ever seen. Because I don't have a good GPU sort solution. So much code just needs to get deleted in this code base. So we're gonna call this that, like, you know, sort occluders. So what's a quick and dirty easy sort algorithm? So basically you need every element to check with every other element, in a sense. And you need to swap until you so hmm. I'm holding myself back from being obsessed with full planet scale terrain. Is what I'm doing. I just got over that stuff. I can't work on. I can work on way more gameplay. Excellent. Yeah, maybe need to devise like a plan on what you want to do. Yeah, there's the bitonic stuff. Yeah, I remember looking to sorting stuff before. Oh, look at this, looks fancy. Um, yeah, I remember looking into this. Yeah, but it has to be power too, doesn't it? Which is not a problem. It's really not a problem. Like, if it is as simple as just grabbing this and chucking it in the shader, then maybe. We don't need a big sort anyway. So you got some LDS. So I've got a hard-coded number of elements. This could just be alright just to use. Unreal 5.4 is doing an add large world coordinate system soon, so like you're tempted to switch over to Unreal because of that reason. But that means you're gonna have a whole simulating world that's running, right? What is the problem? Like, don't you just have like, don't you just or like the problem is floating point, right? Don't you just make everything just shift the origin around when you like get to a new chunk or something like that? I don't see the issue really. Yeah, but maybe that causes problems, and maybe you have to. Yeah, I haven't done it. Um, right, maybe we can take a look into doing this if it's this simple. Each worker must save 2 elements into local memory, as there are twice as many elements as there are workers. Right, okay. Right, and then it will store them into that local memory. We don't have too many, it should be alright. And then what is H? Right, half or something like this. I remember looking at this before and I was like, it was confusing why it worked, because that would half down to 2. And then it would half down to 0. Sorry, half down, so from 2 it then goes down to 1 and 0. And then so I guess, right. Right. Hmm. Let's give this a go and see if it does work. But then like how would you do there's the comparison value and swap. Okay. Let's give it a go. So you have to create a sector system or have high precision on CPU side compared to yeah, since GPU. Right. Yeah, I see. Problem with bitonic stuff is that if the len has to be a multiple of. I don't think it's a multiple. I think it's actually a power of 2. Yeah, it's power of 2. Still though, yeah, I see what you're saying. That's the only problem with it. Luckily, ours is going to be a power of 2 anyway. We will have invalid data then being shifted around. Maybe we just do a proper sort quick. Let's get it in there. What is this one again? Update shader code, which gives you the following update shader. Oh, it is. What did I miss? But is the simpler version just the CPU codes allow larger numbers of sortable elements? Oh right, okay. This won't scale. The implementation is right. Yeah, I know, right? Because I was just thinking maybe this is actually just quite simple to do. Then maybe we just chuck in the simple one that doesn't scale, and it's kind of quick enough for now. I don't know. I don't know. It's been a while since I've written a sort function, so there's probably something simple missing which we could just do. But yes, you know what? It is getting closer to that time, so maybe let's just speak about next time. So next time we're going to sort these occluders, then store the occluders in the volume, and then we're going to write the low resolution renderer, which is going to render the occluders in a low resolution, probably using ray tracing and maybe I don't know exactly, but the thing is we've got to be careful of is these volumes can be skinned. They can have bones and then stuff can move, which means these won't be access line bounding boxes anymore. When we take the occluders and move them into view space. So we might have to use a different strategy on how we render those for that reason, which is going to happen. So yeah, going to be interesting. So we'll do the sort function next time. I'll think of a simple way to do that off stream, and then we'll write a renderer for a low res occlusion buffer render. Pre-sort cluster on XYZ. No, I can't because it's made out of order. It's made on the GPU, so I can't pre-sort it. Yeah. FC implement new features in HTC to support your new simple sort algorithm. Sarcom, no, that won't be the case. I think I'm getting a new version of HTC out soon because I think I fixed all the bugs that I know of. So I need to put a new version out because it's had a lot of fixes. Also, this might help. Radix sort, that's the other one, isn't it? That one does a larger amount of data from what I remember. Also, this might help. It just says some. Yeah, and I know AMD also has their sorting library, but then that's like porting that big thing in. All right. Oh yeah, I love this syntax highlighting. Right, okay. Bit complicated. Yeah, I might just brute force the sorting and just do it in the most terrible way. Maybe. Yeah, thank you for the link. So I'll read up on it off stream. Right, so let's find someone to raid. It is Twitch. Oh, I'm so close. 8 more people. That's all I need. And then we're at 4,000. I might just raid the guy I keep raiding. Because he seems to be the only person making anything in a kind of a low level thing and making their own engine. So this is the way. So yeah, thank you for coming. I'll next be on Sunday. We're gonna work more on this occlusion buffer and hopefully get something on the screen, get some pixels on there. So yeah, I'll see you all in the next one. Have a good start to your weekend, and I'll see you soon.